What happens then? Well, we've captured these grey scale images. We then need to put that onto a computer for us to see. Strictly speaking, the computer doesn't need to make any choice. It can see all of the bands. It's just doing a mathematical analysis. But for us to see things on the screen, we need to be able to visualize that. We need to put that image onto the screen for our eyes to be able to understand it. And we kind of invert the whole thing. We can create colors by we have three color bands being sent to the screen. The screen that you're looking at now relies on, almost certainly relies on red, green, blue color display, RGB. There are a few different variants of this, but they all are basically the same. So that if all three bands are set to 0, your screen will appear black, or a particular pixel on your screen will appear black. Like one of the pixels in this G, these all have a value of 0, 0, 0. 0 in the red, 0 in the green, 0 in the blue. So it ends up looking black. And if we want to create a pixel that is red, then we can maximize the red, say, or some level of red in there. And again, with yellow, we can combine the red and the green to create yellow. And if we want something to be white, like all of this, then we are maximizing the signal that's being sent to the red and the green and the blue, so that the display on the screen looks white. So we can do the same thing with our images, our photographs. This is actually Landsat 7, an older satellite. So the band numbers here don't match what we looked at previously, but rather band 1 is blue. So we start counting at 1 for blue in Landsat 7. We previously looked at Sentinel 2, where band 1 was actually even higher frequency. This one that we don't normally look at. It's for adjusting our images so they mathematically in processing. So ignore that. Let's just look at this Landsat 7 data, where band 1 is the blue light, band 2 is the green light, band 3 is the red light, band 4 is near infrared. And here we have the three colors that are going to be pumped out to our screen, that we can look at on our screens, on our computer screens. So if we just go straight over from this blue here to this blue there, from that green there to that green there, and that red there to that red there, we'll create a so-called true color composite, where the image looks as we would expect it. Here we have some trees, and they're nice and green, and we have some grass, and it's nice and green, and the water is this dark, maybe slightly bluish color, maybe slightly greenish, but it's dark, very dark color. Anyway, so that's our standard color image. And that was done by taking the grayscale information about the blue light captured by the camera, and then pumping that into the blue out onto the screen. And then the same for the green. We took the green grayscale image and pumped it out through the green there and the red. So what happens if we change this, shift things down a step so that the green light goes to the blue? The blue light we ignore. That's forgotten. We drop that. We pump the green light out through the blue. We pump the red light out through the green. And then we pump the near infrared out through the red. Well, then we get this curious looking image. This is a false color composite, and this is a standard, very much a standard false color composite, even used previously before we had digital images, or before they were common, flying using aerial photographs, where you would have camera film that was sensitive to the near infrared light, and you would end up with images looking like this, so that the infrared was presented as red. And that was important because if you remember our spectral signal and the spectral signature, where we have this peak, this very high peak in the near infrared, as being indicative of vegetation. So this is a vegetation false color composite used very much in vegetation mapping. So as we can see, that anything that was green previously is now red, and in fact healthy vegetation tends to look bright red. This is trees tend to have a lot of wood in them, and some of these will be coniferous trees, which tend not to have as much chlorophyll, don't look quite as bright in the near infrared. So we can see that if we then consider this, that we can use different combinations of colors. we can then get an idea of how we can map different types of things using different color combinations. Now this is for us when we visualize something on the screen. As I say, the computer is actually capable of seeing all of these colors at the same time, and so it doesn't need this this separation or this visualization. Although sometimes we do restrict the information that the computer will use for its analysis, simply because one, it can be unnecessary. Two, it can also confuse the maths a little bit. But so if we look, this is now turning back again to Sentinel-2. We can see that that band 1 was this ultraviolet, the very high frequency blue light. That was in band 1. Band 2, vegetation mapping and water penetration. So vegetation, we're using vegetation, we're doing lots of vegetation mapping, simply because we want to, this visible light, and we want to see where things are. But also the vegetation mapping, from, especially with the greens, obviously vegetation is green, so that's a good indicator. But particularly in combination with these infrareds, like the red edge, where we're looking at that jump up. This is our NDVI mapping band. A lot of these will actually work for that. But we also have other details. We can try and get some idea of the health of vegetation by looking at various aspects of the near infrared, what's actually in there. But also, if we're looking for other things, snow and ice, NDSI, for example, works in a similar way, where we can use these bands for that. So just standard combinations for our own eyes to be able to see these images if we want to start mapping. For example, healthy vegetation. Here we're not looking at the visible light at all. Oh, sorry, we do have one band of visible light, but we're actually focused mostly on the near infrared. The combinations, tends to pick up water slightly better. A lot of this is kind of, so some of these small variations might just be personal taste. Some of them are actually quite useful. Some of them you will find more information in some of these other bands. But just for example, you might end up with an image looking like this, the 1211-8A. So this is all in the infrared. Not something that we would typically recognize as being the surface of the. We can perhaps recognize the structures, but the colors are pretty unfamiliar. But that's because we're creating these colors from bands that our eyes can't normally see. Again, here, this is this 11-8-2 combination. The intensity of the colors, the color combinations are not what we would typically expect, simply because we're not looking at the normal light that our eyes are capable of seeing.